when we do the spectroscopy, we try to get these lines, try to measure these lines. And of course, by measuring at various phases, various times, we can know much more information about the particles. This is the zoomed view. So when you plot the spectrum, x-axis you have wavelength, y-axis you have intensity, and you can see that O-type star, B, A, F, G. So as we are going above, the surface temperature increases. You will not see a strong absorption lines. The most famous line is generally is this H alpha line, which is generally seen at 65, 63 angstrom or 653 nanometers. And there are other important lines like H beta line, H alpha line. Of course, you have sodium lines, magnesium lines also, depending on, but generally these hydrogen lines are often seen in many of the stars. So most of the information are relied on these particular stars. And as you can see, this is sort of a black body radiation, which is a characteristic. That's why we apply all the Stephen's law, Stephen Boltzmann law, and all those laws, Planckian function, etc., because they are like quasi black body or black body sources. I would like to, these are the characteristic properties of all these things. Okay. Now, this is a very famous diagram because you might have already heard many of the talks previously. This is known as HR diagram or Hertzsprung-Russell diagram. And you can see that 90% of the stars lies on this yellow patch along this line. Okay, and 10% of the stars, they are on the uh, off diagonal paths, and all these blue region part. This is basically a chart diagram for one of the clusters, stellar cluster M55. Or in general, also if you take most of the stars, they fall on this main sequence, this diagonal part that is known as main sequence phase, where a star spends 90% of its life on this main sequence, and as it evolves, it changes, it moves from to the right of the HR diagram, and then to the left, and it either can become a white box source, or it can become a neutron star, or it can become a black hole source. This is again a very big enhanced picture of the same. So as you can see, the diagonal part, this is this is known as the main sequence stars. And on the right side, you have giants, supergiants, for example, Betelgeuse and all those things. These are general topics like mass of the white dwarfs, neutron star, and black holes. So if you know the mass of white dwarf and neutron star in a binary, the importance is that we can understand what is the equation of state of this white dwarfs and neutron star, which is very, very difficult because we can't make such kind of matter in our lab. So we have to rely on observation of these white dwarfs and neutron stars. And as I think you may, or I don't know whether you know or not, generally these white dwarfs and neutron stars are quite different from our normal stars, because in normal stars, the gravity is balanced by the radiation pressure, whereas in neutron star and white dwarfs, the gravity is actually balanced by something called Fermi pressure. Otherwise, these sources cannot, exist in our nature. And that's where this Chandrasekhar mass limit came into the picture. In his famous work around in 1930s, he showed that such kind of structure are possible. And this is a very famous Chandrasekhar mass limit, because when he derived it is 1.72 solar mass. And I always love to show this equation, why Chandrasekhar mass limit is a constant, because you can see on the right hand side, all terms are either numeric or they are absolute constants, like Planck constant, speed of light, gravity, mass of proton, pi. It happens to be always a constant. So if somebody comes up with new Chandrasekhar mass limit, either we have to change this or we have to change our entire physics. And one more importance of this equation is that why it is important, you can see a 400-year physics is involved on the right hand side of this equation. H bar is coming from quantum mechanics. C is something speed of light, that is coming from special theory of relativity. Capital G is gravitational constant, which Newton gave us around 1600. So you can see 400 physics is actually required to study these white dwarfs or neutrons. more accurate calculations actually show that it is 1.4 solar mass. This is for neutron star equation of state, which is very complex, but this is also known as Tolman and Oppenheimer equation. I suppose that most of you might have seen this beautiful movie which came previously, Oppenheimer, and uh, are my slides moving or not? Because somebody has commented that
No, no,
Sir,
no, they are not
slides
moving.
are not moving, sir.
could be the problem.
Only
Because
stellar spectra we can see, stellar spectra slide.
yeah, it is happening. Now can you see I have moved my slides. Can anybody confirm?
Sir, please, I think share again your slide.
Okay.
Yes, sir. Now it is visible.
Maybe this full screen is giving some problem. I don't know.
Okay.
Can you see the can you see the slide now? It is
Yes, sir.
on
It is. Yes, sir.
Chandrasekhar mass limit.
As spectral type, it is given.
No, 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 no. The slide is Chandrasekhar mass limit.
No, no, it is not, sir.
It is not showing.
No, sir.
My net is very fast.
Just show, just press Shift F5 and then see whether it works or not.
Can you see now? Is it okay?
Yeah, now we can
Yes,
see
sir.
and it is full screen now. Yes.
Yeah, it is visible, sir. Now
Now can
TOV
you see?
equation.
Yeah, TOV equation.
Yes, sir. It is visible now.
Now can you see the white dwarf star equation?
Uh, Say limit for white dwarf. Yes, sir. It is
Yeah, yeah,
visible.
yeah. So this is the equation I was talking about. You can see the right hand side. It is absolute constant. Nothing you can't change nothing. I mean, H Planck constant, that is H bar, C or G. You cannot change anything. It requires 400 of physics because G comes into the picture because of the Newton. H bar is because of the quantum mechanics, and P is because of the quantum mechanics. C is the speed of light, which is again because of the quantum mechanics. So when Chandrasekhar derived it, it is of the order of 1.272 solar mass. But if you consider more advanced astrophysics, it comes out to be 1.4 solar mass. Now I have changed the slide. Can you see it now?
No, sir. It is still TOV equation for
Yeah, yeah,
MS.
TOA equation. Yes, yes, TOA
Yes.
equation.
Okay.
Okay, this is basically equation related to neutron stars. TOV is basically Tolman and Oppenheimer, and V is another person. I hope you might have seen last year one movie came, Oppenheimer. He is like the Manhattan Mission project director, but he also found this equation of state of neutron star, and he proved that the neutron star, the maximum mass of a neutron star cannot be more than 3 solar mass. Otherwise, it will eventually become a black hole. Okay, so this is one of the interesting studies. Okay, now I will skip this. Can you see my next slide? Neutron star pulsar.
Yes, sir. Yes,
Yeah,
sir.
yeah. So she's the lady, Jocelyn Bell, and his boss. So she was the first person. She was a scholar at that time. She was the first person. She detected something called neutron stars, and she found pulses, which is coming from one object. And if you see the periodicity of the pulsar, which happens to be 33 millisecond, and these 33 milliseconds are considered to be the rotational speed of those pulses. And when you calculate those rotational speeds and using some classical formulas, you will see that the radius has to be of the order of 20 kilometers, and mass has to be of the order of less than 3 solar mass, and they term that as pulsars, which are basically neutron stars. So I happened to meet her in one of the conferences in 2014. I hope you can see my slide here. Can anybody
Yeah.
confirm? Yeah.
Yes, sir. Yes.
So the middle one is Jocelyn Bell, and the left side is Professor Sita, Dr. Sita from ISRO. I hope many of the she is the mission. She was member in Chandrayaan in MOM mission. She worked as the project director or assistant project director. So we had a chat at that time. Yeah, so this I will skip the part. These are small calculations. So yeah, now coming to the small black holes. Uh, Now I am on the slide of small black holes. So generally small black holes, the mass range is of the order of 10 to 10 solar mass or 20 solar masses. Okay, sometimes 30 solar masses. Right now we have a confirmation. We have more than 400 more than 400 number of small black holes which we detected in our galaxy. But the confirmation came for only 20 or 30, not more than that. When I say confirmation, confirmation means dynamical confirmation, that is using Kepler laws. We determine the astronomers determine the masses of those binary system, and we confirm that these are actually stellar size mass black holes or 10 solar mass black holes. Actually, we detected 200, 300, but they are indirect methods by which we say that they are black holes. Theoretically speaking, we should see almost all 10 power 6 or let's say 1 million stellar size mass black holes in our galaxy. But we couldn't detect it because most of the time these black holes are in quiescent phase. Quiescent phase means they don't do any activity. They are very quiet. No radiation is coming. Nothing is coming out. Okay. Until unless nothing is coming out. And we know that one of the property of black hole is they don't emit anything. So we are not able to find out. But according to simulations and all, you should have more than 10 power 6 stellar size mass black holes in our galaxy. As I said, it is very difficult to detect. And one more point is, if these black holes are in binary system, we can detect it. Okay. Our lives are very easy if they are in binary systems because the other star, there will be some matter which will be, because of its evolution, the other star will expand. The matter slowly falls into the black hole. And as the matter reaches to the black hole, it eventually emits X-rays. And we can detect X-rays and then we can study the various properties of this. And we can say they are black holes or not. But they are not active, so we have to wait. That's why whenever we go for the space observations, there is always something called all sky monitor with them. And these all sky monitor job is basically they scan the sky every 90 minutes or 2 hours, something like that. And whenever there is a X-ray, sudden X-ray burst or sudden X-ray observations, we use more high sensitive spatial telescopes to pinpoint that and we start studying them. So yeah, I don't know whether my animation is, can you
It
see my
is.
animations?
Yes, yes. It
Yeah,
is
yeah.
working.
So yeah, so you can see here what exactly happens. You have a star which is bulged, matter is leaving from that star. It is going towards a black hole. Of course, this is not a black hole, it's a neutron star simulation, but eventually you can consider that it is a black hole. The matter will form a disk, which we call as the accretion disk, and slowly the matter will fall onto the neutron star. If it is a neutron star, you can see beautiful pulses that at the dipoles you have beautiful pulses. Otherwise, it will simply go into the black hole and the matter will never come. Yeah. So now I've moved to my next slide. You can see these are basically some of the temporal variations of stellar size mass black holes in our galaxy. The name convention are also given. For example, on the left side, second panel, you can see XTEJ 1560 minus 564. This is the name of a black hole. And you can see that most of the time, the X-ray counts are very, very small. It's quiescent. It's very close to zero, so you don't expect anything. But sometimes you can see that the counts are suddenly raised 200, 300. Sometimes they are quiescent. Again, then there is a burst. So you can see that these are few of the black holes which I have shown, almost 6 black holes, light curves. We call it a light curves. So we have to continuously monitor. The idea the basic problem with these black holes is we don't know when they are going to go for high X-ray observed, high X-ray radiations. So we generally continuously monitor them, and whenever there is a activity started, there will be multiple mails or electronic alarms in various observatories, space observatories. They go for it, they continue monitor it. Many of the astronomers write proposals to study them, and that's how we study the properties of these black holes. And so the beauty is, this is very slightly technical, but those who are from physics background and engineering background, they can understand that there is something called signal processing. So in my previous small animation, I've shown that as the matter approaches to the black hole or neutron star, the mass it forms a disk. It has an orbital velocity, and you can see that when you do something called Fourier transformations or power density spectrum, so you can see beautiful peaks. Okay, these are known as quasi-periodic oscillations. That is basically the matter is rapidly oscillating. Okay, and you see the frequency of the earth. It varies from 1 to 10 hertz. Again, by studying these oscillations, we can actually know whether it is a black hole or whether it is a neutron star. The problem, the X-ray view of neutron star and black hole is very similar. But if you do very sharp study of timing characteristics or spectral characteristics, you can actually make a difference by doing this neutron star or a black. So this is sometimes these oscillations appear and disappear very rapidly. Within few hundred seconds, they change. For example, in this slide, you can see there is a QPO here, there is oscillation here, and suddenly it disappeared. So this NQ means no QPO. So there was no QPO. And suddenly as the counts increased, you see a QPO. So there is a physics behind that, why it is happening, why it is not. But basically, if you try to understand this, you can actually know how the matter is behaving very close to these compact objects. Now coming to yeah, well and good. We know that there are stellar mass black holes. We don't have any problem. Okay. We have a very good physics with this. We know how these stellar size mass black holes come, how they are made, how they are produced. We have entire theory. Okay. There are some if and buts, but otherwise on a general scale, we know what is happening. Then there is actually supermassive black holes, which I'll come again later. But supermassive black holes, they exist. We know we have a dynamical confirmation because in 2020, Gezia is one lady and her group, they got Nobel Prize for that. They found supermassive black holes, dynamical confirmation of supermassive black holes at our Milky Way galaxy, which I think I've kept the animation, I'll show you. But in between these small black holes and supermassive black holes, there is something called intermediate mass black holes. And they are more elusive in nature because one of the methods says that they have to be intermediate solar mass black hole. When I say intermediate, that means their mass range has to be from, let's say, 500 solar mass to 10,000 solar mass. Okay, but they are very, very rare. We don't know why they are very rare, but they are very rare. And as I told you previously, that there are other methods to calculate the mass of the black holes. And I have written a very small formula, that is luminosity L is like 10 power 38 times of m by n squared. Okay. So you simply, what we do is we try to measure the luminosity from the spectrum. We take a spectrum, we measure the luminosity. And if you know the luminosity, naturally you can calculate it. This is a very straightforward calculation. Generally, these intermediate mass black holes, which are also known as ULXs, ULX means ultra luminous X-ray sources. ULX means ultra luminous X-ray sources. They emit, their luminosities are very, very high, 10 power, sorry, 10 power 39 to 10 power 41. And if you keep these luminosities here, you will see that they will range from 100 to 10,000 solar mass black hole. Okay. Now the question is, where are they? Has there any observational evidence? Let me tell you, there is hardly any observation evidence which concretely say that there is intermediate mass black holes, but there are indirect evidence which I will show to you. So this is one of the galaxy. This is an interacting galaxy, and all these small dots, what you see, they are basically ULXs. ULXs again means they have very high luminosities. Okay, compared to stellar mass, they have high luminosities. And when you calculate their masses, they are of the order of 100 to 1000 or 2000, 3000 solar mass. Again, you see, this is one of the galaxy, and this is the central region, and this red dot is basically is one of the ALXs. Again, they claim that it is ULX because primarily because of the X-ray luminosities. This is a typical spectrum what we often use. This is emitted by one of the famous source. I don't know whether I've written or not, but if you do the spectral modeling and all, they found that the luminosity is of the order of um, I'm sorry, their luminosity is of the order of 2.3 into 10 power 41, and which amounts to a mass of the black hole, which is 2300 solar mass. We don't know whether there is actually a 2300 solar mass or there is some other physics going on, but this is most probable candidate for an intermediate mass black hole. Yeah. I hope my slides are moving, right? Can
Yes,
anybody?
sir. Yes.
Yeah, yeah.
Moving, sir.
Yeah, so this is a very small work which I done when I was an MSc student in the department. We told that there is no intermediate mass black hole. It is basically the geometry. Okay. So this is actually simple terms. You are not getting the luminosity of 10 power 41. It is actually the luminosity is beamed to you. So basically luminosity is less because it is beamed towards you. You will see a artificially enhanced luminosity. We did this geometrical calculation. We wrote a code. At that time, we wrote a code in C, which ran for, let's say, 2 days to get one curve. We took 2 days to get one curve. And we find that you can explain this luminosity difference. You can explain the luminosities, but if it is just 5 into the baseline of the luminosity, you can explain. If it is 100 times, even this model can't explain at that time. So this was very small MSc project, which, but of course, it came in a very reputed journal, ABJ, of it's in US-based journal. Again, this is again a very famous source, intermediate mass black hole. This is known as Hollock's HLX X1. You can see generally these ULXs are off nuclear sources. So this is a galaxy, edge-on galaxy. This is the center of the galaxy, and it is very close to the center. Not so close, but we can say that. Okay. So this is one of the source, and this source, when you do the Fourier transformation or signaling, you will see beautiful QPOs. So just few slides back, I've shown you some quasi-periodic oscillation. These sources also exhibited quasi-periodic oscillation. And the beauty of this oscillation is that relativistically or classically, these can be connected to the mass of the black hole. Okay. And they found that for this particular source, M82X1, they found that the mass can range from 25 to 500 solar mass. Okay. This was very exciting news at that time. So this is again one of the methods by which uh, you can say that this particular source, that is M82X1, is a intermediate mass black holes. So it is a possibility. We don't know whether it is actually a 500 solar mass because we don't have any dynamical confirmation. We don't know whether there any optical counterpart. If it is an optical counterpart, how to find out what is the orbital period, etc., etc. It's very complicated. X-ray observations can directly give you a direct hint. That's why we study these X-rays. Achha, this is a very interesting work came in Nature last year or last to last year. This is a you can see this is a cluster which is one of the biggest cluster in our galaxy. This is known as Omega Centauri. I'm sorry for the spelling mistake. This is Omega Centauri, and it's a very big cluster. It's a dense packed uh, hundreds of thousands of stars. It generally these clusters are spherical in shape. They always stay very close to the galactic center, close to the galactic center. And it has been debated from last 2 decades or 3 decades that this particular cluster should have a black hole at the center. So you can see the zoomed version. This is the entire cluster. This is the zoomed version. This is the center part of that. Again, you zoom it. So people said that there is a likely a chance that if there is a black hole, you should have a black hole at this part, at this center. Let me tell you, the size is very, very small. It's like 0.1 or 1 light year. So what they did was they done a very good job. What they studied, see, black holes, we cannot see it because it does not emit any light, but it has a gravity. And the stars around it will experience the gravity of this. Okay. So they studied the stars which is very close to that particular central point, which I have shown you in the earlier slide. So around these stars, they have studied it. And this is the Hubble Space Telescope images. See, they studied from 2002 to 2023. I cannot see, it's 2000 or something. Yeah, 2002 to 2023. So this is the black hole. These are the two stars which are above and below. You can see in the diagram. Now, if you carefully observe, you can see that by 2023, there is a change in the position of these two stars. Okay. And let me tell you, the star position change is purely assuming that their stars are, the star position has changed because of the gravitational effects of this central black hole. And then they perform all the calculations and they found that, I will not go into the details, but they found that if the stars have changed its positions because of the black hole which is present, then the black hole mass should be of the order of 8,200 solar mass to 40,000 solar mass. Okay. So what basically they studied is, they studied the change in the position of these two stars and they calculated something called escape velocity. Okay. And if they... Hello. Shall I continue? Hello. Can anybody?
Yes, please continue.
Yes, sir. Yes, sir.
Yes,
Please
yes.
continue.
Sorry, sir. So, so if there is no black hole, this line, this red, this blue and black lines, flat, constant lines, they are actually no black hole velocity. If there is no black hole and they are orbiting, that is this is a theoretical line. These stars, these magenta fast stars, when they observationally calculated, they found that the escape velocity of these stars are above 80 or 60. Okay. And these curves, what you see, these curves, blue line and black dashed line, if you try to fit that, you have to fit at least the mass of the black hole has to be 8,200 to 40,000 solar mass. And this is a very strong, I mean, let me say, this is the strongest observational evidence till now that there is a intermediate mass black hole which exists in our nature, and this will be one of the concrete evidence for the existence of the intermediate mass black hole. Let me tell you, if this group or any other group can confirm this, maybe after 10 years, this work can be nominated for the Nobel Prize. So that is the essence of this work. Okay. Still, there are some errors are going on, but this is to date is the best example that there exists a intermediate mass black. Now coming to the supermassive black holes, there are galaxies with so these are the galaxies. This is the size of the galaxy, and now we know that every galaxy center we have a black hole whose mass is greater than 10 power 6 solar mass, 10 power 6 to 10 power 9, sometimes 10 power 11. So it ranges 1 million to 1 billion, something like that. Now, How they came,
Not non-mobile ಅಲ್ಲ.
how they came, what is their formation technique, what is their formation mechanism, at what redshift they form. I mean, at what when the universe was young, what is the age of that universe when these supermassive black hole forms. All these are open questions. Nobody exactly knows. Some people say that they are primordial black holes. Primordial means they already exist in the universe and somehow matter came to it and all this galaxy formation came into the picture, but exactly we don't know. Okay. So this is a very famous source, 3C273. You can see that this is a radio telescope. This is Cygnus A. The central region is this central region is the visible galaxy. See, this is the visible galaxy. I'm talking about galaxy here. I'm not even talking about supermassive black hole, which will be somewhere at the center of this source. Supermassive black holes are very dense object. They occupy very small region of that galaxy. Not even 1%, let me tell you, not even 1%. And but its activity is so huge. So this is the entire galaxy, and these are the radio lobes. So the idea is that some activity very close to the supermassive black hole is emitting lots of jets, lots of flows out. So they are going outward, they are hitting some hydrogen gas, which is already present here, and it is ionizing. That's why these you see as hot lobes here, which can be detected in radio, not in any other. And there are there you if your eyes are very good, you can see small jets like structure. So matter is ejected in this jet like structure. So they are enigmatic. Without black holes, let me tell you, you cannot have star formation in a galaxy. There will be no activity. So actually black holes are good because they help us to they help in forming a star or star birth take place. Now how to know the mass of the black hole? Now this is, I don't know whether the can you see the animation? It is running now.
Yes,
Yes,
sir.
yes, it
Yeah.
is.
This is the Milky Way center, which we are right now watching. This is an animation. And now we have a more advanced animation, but these are all real observations. Okay. So what you have observed is that the observation started from 1992 and they studied uh, to the center, which is located in the Sagittarius A. So that plus mark is your supermassive black hole in our Milky Way. So what we study is we study these star orbits. For example, this particular star, there is a complete orbit. So we try to measure A, that is semi-major axis of this orbit. We measure the time for particularly this star. If I remember, it is 15 years. We know semi-major axis. We know its eccentricity. We simply use Kepler's law and we found that Milky Way center, the supermassive black hole mass is of the order of 4 million solar mass, 4 into 10 power 6 solar mass. And for this work, Gezas and her team in 2020, if I'm right, they got Nobel Prize for this work. This is the first dynamical confirmation that supermassive black hole exists. Of course, for other galaxies, we cannot do or cannot perform such kind of studies because your resolution has to be very, very high. Even with the 100-meter or 200-meter telescope also cannot do that. So we have to rely on some other methods. What is the other method? One of the method is this is a typical spectrum of AGN, or you say typically for very active black holes or active galaxies, you will see many lines: carbon line, magnesium line, oxygen lines, H alpha lines. We try to study the width of these lines, and by measuring the width of these lines, we can know what is the mass. These are my works in 2022, 2023. We studied almost 3000 AGNs, active galactic nuclei, that is basically supermassive black holes, where a lot of X-ray emissions or optical emissions are coming. And we analyzed almost 15,000 spectral lines, and we determined the mass of the black hole, and we studied various parameters of those galaxies or activity. And so If you measure these lines width, if you do proper modeling of the spectral lines, we can actually measure the masses of those black holes. This is again another method, but this is very complicated, but I don't want to continue. But this also I work, this is known as, again, by doing the cross spectral density and all, we can again study these masses. Yeah, this is my recent work, which actually came in. This is like discovery of an ultra fast outflow UFO in one of the galaxy named IRAS F123097, etc. This is my recent work. It got media attention also recently. And what we found, if you carefully see, this is a spectrum of that particular galaxy or active galactic nuclei, that is the central region of the galaxy. We see these two lines. Okay. One line is at 8 kV, another line is at 9.5 kV. And actually, these lines should occur at 6.97. That's what I have written. This line should occur at 6.97 kV, but we observed at 8 kV. So there is a blue shift. That means this line got some energy and it is appearing at 8 kV. And the interpretation goes as that these lines actually, blue shift. There is something called red shift and blue shift. It got blue shifted because there is a strong wind which is present in this particular source. So it was not discovered earlier. Suddenly we were lucky to get this discovery from when we got this result, we actually were surprised actually. How can somebody missed such an important piece of information? And we reported immediately to that particular journal, ABJ, and it got, within 20 days, we got this acceptance from that journal. Yes, there is a discovery event of. And the more interesting point is that this is 2005 observation. You can see these two lines, whereas in 2019 observations, there is no line actually. There is nothing. I mean, one can argue this. There is a one single point, but we don't rely on single points. So that means that winds are changing, the speed, the outflows or the wind speeds has lot decreased because of some mechanism. Still, we don't know what happened to that, but still we are working on that. What causes the sudden disappearance? When I say sudden, we can see here from 2005 to 2019, there is only 14 years, but on a cosmic time scale, 14 years is very short time. So we are studying on why this happened, why suddenly the outflows have disappeared. And let me tell you, these outflows are extremely important for star formation. If you don't have outflows, the star formation rate will be very, very small. This is a typical optical image of this particular source where I want to show that this is the optical image, and generally they keep a slit here and they try to study the spectrum, and by analyzing the spectrum we can know the mass. This is also interesting source because the mass of this black hole and the mass of a Milky Way black hole, they are same. When we measured the mass of this black hole is of the order of 6 into 10 power 6, whereas our Milky Way mass is 4 into 10 power 6. So they are sort of close. Of course, we also detected these blue shifted lines in soft X-rays also. Like this is 1 point. We have seen that this is at 1.3 kV. Actually, this line should be somewhere here, 1.2 kV. It got shifted. Okay, and we interpret it as that the shift is because of the winds which are going, they are moving towards us. So that's why with speeds of 30% of the speed of light. So the winds are very fast. 30% of speed of light is very, very fast. 60,000 or 70,000 kilometers per second. They are very fast. Again, you can see that in 2019, this particular line is not there. Okay, this particular line is again disappearing. So take home, this is, sorry, I've written workshop. So this is a very fascinating subject. Any youngster can work on this field. There is an Indian satellite also, which is studying, which is known as AstroSat, which is still working in space and giving lots of data. and the data is open to public. Anybody can analyze and all those things. Yeah, thanks. So here I will stop my talk. Thank you very much.
Thank you very much, Dr. Sri Ram, for this exciting talk regarding all types of black holes.
Yeah. Thank you, everyone.
Now, before going ahead, we invite all the for their questions or
Sure.
queries regarding this.
Yeah.
Hello, good evening, sir.
Good evening, madam.
Yes, please go ahead. Good evening.
Sir, I have one. In fact, I
Madam
have a
Amoli?
few questions.
Yeah.
Sir, is a black hole some kind of a wormhole?
No. The basic difference between a black hole and a wormhole is black hole absorbs it doesn't absorb. Whatever fall into this black hole will never come out. It absorbs, okay? White hole is something which is ejecting matter away out. Okay.
Yeah.
And one more point about wormhole is that wormhole is a theoretical object. Nobody has observed wormholes yet. Okay, there is a study which says that wormholes, even if they exist, they are very unstable object. Within universe time scale, they will disappear. Okay, so we don't have any observational proofs that there are wormholes, but we have lot of observational proofs where we have black holes.
Right. And sir, how do the black hole
Omkar?
jets form, and actually why are the jets why are they so energetic?
Yeah,
What
answer.
gives them the thrust?
Purely speaking, madam, we don't know the exact physics. There are probably one very strong theory. The theory is that as the matter forms an accretion disk, there are something called magnetic field of lines, which are vertical in nature. Somehow this accreting material, they allow to this magnetic field of lines. And there is a theory which says that it takes the angular momentum from the spin of the black holes. Because these supermassive black holes are black holes, they have a spin and their relativistic spins, 0.9 or 99% the speed of light. So these matter, these magnetic fields along the matter, they take some of the momentum from that magnetic field of lines and they shoot out as jets. And their speeds are enormous, they are relativistic, sometimes 99% of the speed of light. This is a theory.
Okay.
Yeah.
Okay.
Most of the...
Sir, one more question.
Sure.
We know that black holes have very high gravitational field.
Yes.
And does the
then
black hole
like it
also
ಗೊತ್ತಾಗ್ಲಿಲ್ಲ.
have magnetic fields?
Madam, can you repeat your question? Somehow I couldn't hear you. Can you repeat your question, madam?
The question is, we know that black holes are having gravitational field, very strong gravitational field.
Yes.
But do they have magnetic fields also, very high magnetic fields?
No. Black hole doesn't have any magnetic field or electric field. The matter which is nearby, they have magnetic fields.
Okay.
Right.
Okay, sir. Thank you.
Thank you, madam. Sir, Arvind sir.
Sir,
you were there.
One question in my mind is that one side we say that nothing can come out from black hole.
Yeah.
And other side we say some jets are emitted by black hole.
No. Jets are not emitted by a black hole. Jets are not emitted by a black hole. Jets are something very close to the black hole. And the matter which is interacting, sometimes they can exchange the spin angular momentum of the black hole. Nothing is coming out from the black hole. Jets are very close to the black hole. That's what I'm saying.
Okay.
Sir, does that mean that we know about the 4 dimensions, that is X, Y, space and time? Does that mean that the black hole is having some 5th dimension also?
Madam, theoretically, we have many dimensions. 11 dimensions are there.
Yeah.
But the problem is we cannot see it. That is the biggest challenge we have. As you said, observationally, we have to work with X, Y, Z, and T. We don't know about other dimensions. They are very, very small as per the string theory. We don't have any observational proof for that.
Okay. Okay.
Right.
Thank you.
Thank you.
Any other question? Dr. Kulkarni, yes, please. I think some signal issue is there with
Yeah,
Dr.
yeah.
Kulkarni.
So I think so you can type in the message.
Okay. Yes, Dr. Kulkarni, can you hear us?
Sir,
Yes, Yadavi, your question. Yadavi, ask your question, please.
sir, is a white holes exist?
As I told, white holes or wormholes, they are theoretical objects. They are used for conserving the black hole. Okay. Because we want to satisfy some of the equation in mathematics. So that eventually led us to something called wormholes or white holes. But the problem is, first problem is we have never observed any white holes or wormholes. Second is there are some research work done in wormholes which says that they are not stabilized objects. Okay, even if they exist, they will they will not be stable and they will collapse. So we don't have any observational evidence of wormholes.
Okay, sir.
Right.
Sir, I have a question.
Yes, Dr. Kulkarni.
Sir, I have a question.
Yes, we have with us Dr. P.K. Aluwalia, sir.
Acha, somebody asked Siddhant Bose, can a black hole shrink? No, sir, black hole cannot shrink. As per the Stephen Hawking area theorem, whatever the matter goes inside, its job is to increase the area of the black hole. So the black hole once formed, and when you have matter going inside, always the surface area will increase. So there is no possibility that it will shrink more. The area will increase more. The mass has to be more. It will increase, not decrease. This is the famous Stephen Hawking area theorem, which doesn't allow it to shrink. I hope I
Sir,
have given the answer.
if I may ask that you just said that the black hole's mass would increase, but
No.
how do we
Black hole
actually know what
mass,
is the mass?
black hole mass always increases. It will never decrease.
So, but how do we know what would be the actual mass of the black hole? Have you ever calculated it?
Yes. We have calculation.
Do we have an idea that what is the mass of a black hole?
Yes, we have. Stellar mass, black hole masses, we have dynamically confirmed, for which Nobel Prize was given. For Milky Way center supermassive black hole, we have dynamical confirmation that it is a mass of 4 into 10 power 6. So we have measured it. We know what are the masses of these black holes. So very high precision.
Okay. Okay.
So now I invite Dr. P.K. Aluwalia, sir, for
Thank you. Thank you very much. Thank you. May I speak?
Yes, sir. Please continue.
Okay. Yeah.
Yes, sir, please.
First of all, greetings from Indian Association of Physics Teachers. Thank you very much for sparing your time.
Thank you, sir.
Because what we feel is that through this effort, we are creating a resource for a community of physics students and teachers so that they can understand various aspects of the astronomical problems which are being studied at present, and the excitement around them. And I would be very happy to tell you that last year, when we ended this series, we published a small booklet, thanks to uh, Professor Hemant, called Cosmic Conversations. And in each page, we had provided a QR code for watching the uh, YouTube link itself. So this is the idea behind this, because there are certain things which are happening around in the country which are very exciting, particularly with the coming up of 4-year research degree program at undergraduate level. We find that we have to tell our students and teachers what are the possible projects which they can do. And today, when you gave that task as task for home, I think that was in that spirit only.
Yeah.
I really loved it. I really loved it when you said that. And
To add these points, let me tell you, sir.
yes.
I heard Kasturi Rangan sir speaking in one of the occasion, and he told that the space science is going to be the next big science. Let's say at
Yes.
least for next 500 years. And you can see how the space tech companies are mushrooming throughout the world. At Hyderabad itself, we have 5 space tech companies. Of course,
Yes.
right now they are not doing any astronomy or space science, but it has started. Let me tell you, 20 years back, if you see all the IITs, there is no astronomy in IITs 20 years back. Now, if you go to any IIT, NITs, ICERs, any national institute, there is always a astronomy department or space science department. So it's
Yes.
a next big thing, or because astronomy is not a subject by itself. We require maths, physics, software, computer science, electronics, mechanical engineering, electrical engineers. Everybody, if they feed it, then you can make your instrument, and that instrument has to be flown out. And then you study various sun or any other thing. One of my friend who recently visited from NASA to Usmania University. So I was talking about that. What is the next decade big science what NASA is planning? And he was told that it is the space science or space weather, something we call space weather. Then the reason he told was very exciting because now everybody want to go to space.
Yes.
Everybody, why not for doing science? Science is the second thing. The primary thing is tourism. They want to establish for Elon Musk want to put a mobile tower on moon. Everybody will do that. It will be like, after if we have a very good technology in space, within 50 years we can have a tourism on moon or some orbit around Earth through 3 orbits again come back. So with that sense, that's very good topic. So space weather is going to be a very big thing. So already India is working on it. Already there is a space mission called Aditya, which is studying all these things.
Yes. Yes.
But for youngsters, space science is going to become a very big job opportunity, not in government sectors. That's why ISRO has planned space technologies private. 2-3 years back, they have given go for privatization. ISRO cannot. ISRO has to think after 100 years. Right now, go for privatization. That means all the rocket launching, etc., they will be privatized. And within 10 years, private companies will start launching the vehicles. Already, US has been doing, Europe has been doing, Japan has successfully launched a private vehicle. So it's a booming subject. So all
Yeah.
the youngsters, those who are doing, they can do it. Second
Yes.
point,
Yes.
what I want to know, most of the astronomical data is public domain. Okay, and they can analyze, they can learn, or they can get the guidance also.
Yeah. Thank you very much. I think this is very exciting. Sir Arvind, please mute yourself. Otherwise, there is a mismixing. Yeah. As I was saying, Professor Arvind, please mute yourself. Hemanji, can you please mute him?
Yes, sir. Just a minute, sir.
Yeah.
Yes, sir.
May I start?
Yes, sir.
Yeah. So what I was saying was the following. Yes. May I continue Dr. Sriram, are
Yes,
you
sir.
able
Please.
to hear me?
Yes, you are audible, sir.
Okay, fine. So thank you very much, Dr. Sriram, for enlightening on this. And there is one take which I really would really mention here, as you brought in the name of Professor Kasturi Rangan. He was, in fact, the architect of the new education policy. He was the chairperson of that group which formulated the national education policy. And I think his stamp is visible in that when we look at the way research has been made part of the undergraduate curriculum itself. And I think the talks, the way you have presented today, these are very exciting topics. And I remember you brought in Professor S. Chandrasekhar's name, and he had written a great book on black holes, which is a kind of a masterpiece. And I think this is very exciting if we can really continue with these kinds of seminars, stealing your time to come to us and enlighten our students. So please don't worry about the audience may be less, but our purpose gets served a lot because there are lots of hits which happen when this lecture gets posted on the YouTube channel of NASNI itself. So once again, I thank you very much on behalf of IAPT. Hope you will keep on obliging us in future also. Thank you
Sure,
very
sure.
much.
Thank you. Thank you for the invitation.
Thank you very
And
much,
I
sir.
think I readily accepted the invitation. And
Yeah.
what I want to point out that number of participants are not less, sir. I have given a talk in Japan. There was only two participants at that time. So
Mm.
it is not the participant. Participant is curious as to listen to you or not. That is much more important.
Yes, yes,
Even
yes.
for one student also, if he listens, I will give a
Yes,
talk.
yes, yes,
So
yes. And
so participants,
mm,
number of participants, they are very healthy. Like I can see 20. So they are very
yes,
healthy
yes,
for
yes.
me.
S. Chandrasekhar taught two students who later
Yeah,
won
yeah.
Nobel Prize before him. And he
Yes,
used
yes,
to go, I think, 100 miles to teach them.
yes, yes.
So thank you very much. Great.
Thank you. Thank you, Aliwal. Yes. Thank you, Hemant sir,
Thank you very much,
Kulkarni
sir.
sir, and all.
Thank you very much, sir. Now, Dr. Kulkarni, can you hear us? Please go ahead. Dr. Kulkarni, please unmute, sir. Some serious signal issue is there, I think.
Hemant sir, I think
Kulkarni,
so
sir.
you unmute him. You try to unmute him, and then I hope so he'll be able to.
Okay. Arvind, sir. I cannot unmute. He has to unmute himself. I
Okay.
can.
I
Yes, yes,
it
please.
is unfortunate I missed Dr. Sriram's presentation because of some technical itch. I moved my place about a furlong away and I had some difficulty. Last 10 minutes I could get, but I will see the video and comment on that, okay? It's a great thing that Dr. Sriram came and addressed our gathering, and I'm very happy about it. I think this way I was particularly happy to introduce because I studied in the same institution that he is studying and he is working, and I missed the pleasure. But in any case, the lecture was good, and I will see the thing later. Thank you very much, Dr. Sriram, and everyone else. Thank you.
Thank you very much.
Thank
Thank
you,
you.
Kulkarni sir.
Yeah, thank you.
So finally, on behalf of NASNI, I extend heartfelt thanks to Dr. Sri Ram for sparing time and for telling us about unrevealing mysteries of black holes. Earlier, I heard only black hole. Now, today, I also know small, intermediate, big, and the big black holes. They have also different categories. And you have explained all intricacies of these black holes, sir. And it is as Dr. Aluwalia sir told that it is a big resource for our IAPT, which you have given us. And thank you very much. Thanks to Dr. Aluwalia sir, Dr. Kulkarni, Madam Deka, Madam Amoli, and all Dr. Pranita, and all the students and audience present today with us on this 12th talk. We have completed 12 talks of this year also, and it is a mix of all subjects of astronomy we have done. And we are looking forward for more variety of astronomy in our NASNI group. And Dr. Sriram, actually, we have a lot of students connected from Professor Rajinder Singh Science Exploratory Nagpur. They are sitting together in the class and they are listening you, and they are very excited and young enthusiast, astronomy enthusiast.
Yeah.
They take very much interest in observational astronomy and star parties, but they have very curious and very interesting questions also. They used to ask us, and we ask experts like you. So thank you all. Thank you very much for making this series of talks continue on NASNI group. And we will invite Dr. Sriram again on some other topic, and we will listen him for his expertise on astronomy. Thank you very much. Thank you all.
Thank you very much, sir. I
I would
love
like
to give another talk on some other topic. No issue.
Thank you so much. Thank you so much, sir.
Right.
Now we
Hemant sir,
sign
I
off.
would just like to
Yes,
add one more thing. I think
yes,
so
please.
for the topics like black holes or any other topics, I think so one session is not at all enough. We want some more sessions on the same topic so that we can get
Okay,
deep dive into the information.
right, right. Okay. We will try, madam. Yes. Thank you very much. Thank you. Thank you all. Good night.